Hello, everyone. Today we're presenting our process control project. It's a self-watering plant done by Mohammed Wade and Michael. So to begin, the introduction is so the amount of water needed for each plant varies with their type, and some having narrow range of allowable moisture for their optimal growth. Amount of available water in the soil depends on the soil composition and the humidity of the ambient air. Objective is to create a controller which predicts water loss by absorption and evaporation, measure current moisture levels, and supply a response using a feedback loop that will keep the soil moisture at the optimal set point. Next is the theory. The system is controlled by a theoretical on-off valve. Relative humidity, soil porosity, and evaporation rate are assumed to be constant in this project. We're working with an open loop system, has no pumps. Water flow rate is set constant at 9 milliliters per minute. Moisture level in the soil is measured by portable soil moisture meter, controlled using FOPDT model. Evaporation effects could cause dynamic self-regulating behavior. Next.
Yes, so the first step for our process model is to measure the response with our controller at 100% and at 0%, since those are our two options, either on or off. And since we didn't have a physics-based model that was simple enough to use, modeling the travel of moisture through the soil, we use a step test and measure the moisture level over time. And we found out that the model that we currently have needs to be a higher order and is non-integrating because of the evaporation effects. Nonetheless, we still wanted to find initial parameters that would help us later, and so we used FOPDT, a first order plus dead time model, to fit our process data as best we could. And although it was inaccurate, it was a good starting point for us. And so the next step was to optimize it. We used sum of squared error and got much better fit. And we got these parameters, and the fit is shown on the screen.
And once we got those parameters, we were able to implement them in a PI controller for the non-integrating system. We used a conservative IMC correlation, which resulted in overshoot in the initial testing of our simulation. But with some parameter tuning, we were able to reduce that overshoot by adjusting the tau time constant. We realized along with that the Kc value, or the gain, had no effect on the controller response, which makes sense because our controller output is either on or off and nothing in between. And so when we change the tau time constant, we can see there's a lot of different oscillatory behavior, and that is due to the fact that our model is treating the evaporation rate as the same as the soil saturation rate, which isn't true in real life. The evaporation rate is much slower than when the wetting stage is, but here shows that response more clearly in the controller and in the moisture level percent.
Okay, for the controller performance, the controller was tested with a set point of 80%, which was recommended by the moisture level basically by adding water according to the controller output and measuring the moisture level. The controller reached the set point quickly, but had significant overshoot as shown in the plots. So in conclusion, our controller was a highly simplified version of the complex physical system. However, it performed relatively well with gathered data. Improvements to the design could be made by switching to a closed loop system with an Arduino interface and micro pumps. Additionally, higher order controller models would better fit this dynamic system. An improved control system has the potential to optimize water usage globally and limit the environmental impact of agriculture irrigation usage, while at the same time protecting the beloved houseplants in individuals' homes. Thank you.